Yes, it's my pleasure to present this research work on titanium oxide nanotube films decorated with beta-gallium oxide nanoparticles for photoelectrolysis of water from the University of Joseph Sawataka University, Makurdi, Nigeria. Fossil fuel is gradually depleting due to increased human population and the emission of harmful products from automobiles is causing environmental pollution. Also, the increase in industrialization has increased the rate of discharge of industrial harmful waste products into the environment that are contaminating the environment. And therefore, there is need to look for technologies that can be able to harness clean energy to power our vehicles and industrial machines, and also that can be able to degrade harmful waste products before they are discharged into the environment. And solar energy is an abundant natural resource that can be harnessed and be utilized for solar cells and also for photoelectrochemical water splitting towards hydrogen fuel production. And the mass production of hydrogen fuel is still a challenge due to the low efficiency of photocatalysts. And research is ongoing to look for efficient photocatalysts that can be able to yield much hydrogen volume during water splitting. Also, these photocatalysts can also be used, like I said, for photodegradation of harmful waste industrial products like methyl blue orange and other dyes from the industry before they are discharged to minimize or to mitigate industrial environmental pollution. So titanium oxide has been the first material that was reported for photoelectrochemical water splitting. Titanium oxide has a suitable band age alignment that can support water splitting, but its efficiency is low due to its wide bandgap of 3.2 electron volts. And because of this, different methods are being exploited to see how to improve the efficiency of titanium oxide for water splitting and for photocatalytic degradation of industrial waste. Different methods have been used to produce different morphologies that can tune the efficiency of this material. Also, surface modification or decoration with metals and metal oxide had also been applied. Also, heterojunctions have also been created to create an interface between these semiconductor materials that can boost charge carrier separation and transport towards efficient water splitting and for degradation of harmful industrial products. Also, doping has also been used. So the surface of titanium oxide nanotube films has rarely been decorated with gallium oxide nanoparticles. There are works that have reported its decoration by platinum, gold, silver, and all that. But research is really available for the decoration of titanium oxide nanotube with gallium oxide. So in this work, we have fabricated gallium oxide decorated titanium oxide nanotube photoelectrode by a two-step anodization process followed by a CVD method towards photoelectrochemical measurement in 1 molar hydrogen chloride solution. Materials and methods. We made use of titanium foil of the stated thickness and purity of 99.7%. And the titanium foil was cut into pieces of size 1.5 by 1.5 cm as the substrate for the anodization in order to produce the titanium nanotubes. So an organic electrolyte was prepared by mixing ammonium fluoride and water, deionized water, ethylene glycol, and which was deployed for the anodization. So the obtained titanium nanotube films were of amorphous nature and were therefore annealed in a horizontal tube furnace at 550 degrees Celsius under the supply of nitrogen and water vapor for 3 hours to convert it to crystalline. So after that, gallium oxide was then decorated on this, and figure 1 shows for the decoration of the gallium oxide nanoparticle. Figure 2 is a typical Hello? Hello?
Hi, I think the internet is really bad. You keep cutting off, but please carry on. Thank you.
Okay. So figure 1 shows the image of the horizontal tube furnace that was used to decorate gallium oxide nanoparticles on the titanium oxide nanotube. While figure 2 is a typical 3-electrode photoelectrochemical cell that was used for the photoelectrochemical measurement. The cell comprises of the titanium oxide nanotubes decorated gallium oxide as the working electrode, and then the silver chloride reference electrode, and the platinum wire as the counter electrode. Results. Figure 3 here is the crystal structure of the prepared materials. So the first diffraction, X-ray diffraction, is the XRD pattern of the titanium oxide nanotube that was obtained at 550 degrees Celsius without being modified. While the pattern 2, which is the TNT GNP, is the XRD pattern of the titanium oxide nanoparticle that is decorated with gallium oxide. Surface morphology analysis. Figure 4 shows the surface morphology of the prepared titanium oxide nanotube films. Now, figure 4B and 4D shows the lateral view of the obtained titanium oxide nanotube films. It can be seen from figure 4C and 4D that some small white particles are seen on the surface of the nanotubes, which is the gallium oxide that was decorated on the surface. And then figure 5 shows the elemental mapping, showing the various elements such as titanium oxide, oxygen, and gallium. Figure 6 is the EDX, showing the elemental composition and the spectrographs of the prepared films. It can be seen that there is no gallium oxide on the figure 6A. But for figure 6B, gallium oxide is available because of its decoration on the titanium oxide nanotube films. Figure 7 is the optical reflectance measurement. Figure 7A is the reflectance measurement. Now we use the Kubeker-Monk function to convert it in order to calculate the band gap, as can be seen in figure 4B, in figure 7B. The band gap of the ordinary titanium or the bare titanium oxide nanotube was 3.44 electron volt. Upon decoration of gallium oxide on the surface, it can be seen that the band gap has slightly increased to 3.57 electron volt. This is because gallium oxide is a wide band gap material as compared to titanium oxide. So if it is added or incorporated into titanium oxide, it is likely to increase its band gap. That is why the band gap has slightly increased due to the nanoparticles effect. Figure 8 is the photoelectrochemical measurement. Figure 8A shows the current density in from the recorded from the voltammographs, it can be seen that the dark current is quite low, less than 100 microampere. But upon UV light illumination using a 150 watt xenon lamp, the photocurrent density of the bare titanium oxide increased close to 600 microamperes, while that of the decorated sample increased close to 800, showing that the prepared material is photosensitive, and the decoration of the nanotubes with gallium oxide has really enhanced the efficiency due to the creation of heterojunctions at the point where the particles have contact with the nanotubes to improve the charge carrier separation and transport. Now we check the stability of the system by doing chronoamperometry measurements, as can be shown in figure 8B. It can be seen that the performance is quite stable over a wide range of 500 seconds. As can be seen, the result correlates with that of with that recorded from the voltammograph, as the decorated film has higher transient photocurrent as compared to that of the bare titanium oxide nanotube. We compare our result with that of other works, related works in the literature. And as can be seen in this table, we can observe that our material has performed reasonably as compared to other passivated or surface modified titanium oxide nanotubes for water splitting. As I said, this is the first time titanium oxide nanotube is decorated with gallium oxide, and they're showing reasonable performance, proving that gallium oxide is suitable to improve the efficiency of titanium oxide towards water splitting and for photodegradation. In order to further understand the charge carrier transport and resistance or impedance in the system, we carried out electrochemical impedance measurement. And in order to understand the charge carrier transport resistance, we simulated a circuit, which is shown in figure 9B. And we discovered that the charge transfer resistance for the decorated film was low, which is about 13.12 kilo ohms compared to that of the bare titanium oxide, which shows why the decorated film produce higher photocurrent density as compared to the bare film. Figure 10 shows the body plot, which we now use to study the electron lifetime during illumination. And it is observed that the decorated film exhibit a higher electron lifetime, which it shows why it has higher stability and show higher performance in the voltammographs. Now, the water splitting mechanism is as depicted in figure 10. Yes, because the nanoparticles are in contact with the nanotubes, when the material is illuminated with UV light, the electrons and holes are excited, and then the electrons are transferred from the gallium oxide into the conduction band of the titanium oxide, while the holes from titanium oxide are transferred to the valence band of the beta gallium oxide. So the building field at the interface now boost the charge carrier separation and transport towards improved water splitting properties. Upon elimination, the electrons from the working electrode are transferred through the external circuit to the counter electrode, whereby the water undergoes reduction reaction to produce the hydrogen. While at the working electrode, which is the film, the water is oxidized to release oxygen. And in conclusion, the effect of gallium nanoparticle decoration on the surface of titanium oxide nanoparticles, nanotubes, has proved to be effective to enhance the photoelectrochemical activity of the material. The titanium oxide nanotube decorated gallium oxide nanoparticles produce a relatively higher photocurrent density of about 805 microampere centimeter square, and a photon to current conversion efficiency of 0.32% as compared to the bare titanium oxide nanotubes. So the enhanced photocurrent density observed for the nanocomposite could be traced to the improved number of photogenerated carriers, improved carrier separation and transport, and longer electron lifetime. This work, we have been able to publish it in Solar Energy. Thank you for listening.
Thank you very much for that. Thank you. What I'd like to do, if the person is, if Mohammed Ba is still here, if that presentation can happen now, please. Thank you.